Okay, let's take a look at some simple sizing first, a way that you can quickly get an estimate about what your vehicle weight is going to be. Now, if you recall, we developed this basic weight breakdown where we take the gross takeoff weight of the vehicle and we separate it into basic components of the aircraft: structure, payload, fuel, engine, avionics. There's just one way to do it. There are different ways you can group these things, but generally speaking, this is the most common way. Now what we can do then is we can take an element that we can segment a known weight factor from based upon that individual element weight, and the gross takeoff weight based upon benchmarking numbers or physics. In this case, we'll use benchmarking. That tends to be much more reliable, using previously developed systems to be able to get this number. Best example of this is the weight of the aircraft structure, where we get this structure factor from. Typical values are going to range around 0.3 or so for most vehicles, give or take. So you have to be really careful with that estimate. Then what we can do is we rearrange, and so given a structure factor for a certain vehicle classification and things such as known payload, estimates of the fuel, estimates of the engine, we can come up with gross takeoff weight. Now this is what we utilize for our ITER-TAL spreadsheet, but to determine the fuel we have to get an estimate of how much fuel we actually burn over an entire mission, and that's where we break up the mission profile. So we have to take each one of these segments, determine how long we're going to be taxiing, how long we're going to be climbing, how long we're cruising, and then estimates of how much fuel we're going to be burning in each one of those segments. Then we can put all those together, iterate it, and come up with an estimate. So we're already familiar with this, but I also want to demonstrate a pretty simple back of the envelope method that we can utilize to calculate the weight as well. So I'm going to do this through an example. This is kind of the easiest illustration to do this. So let's consider a UAV that's going to be designed for short takeoff and vertical landing operation with a design thrust to weight ratio of 1. That's actually a little low for a vertical takeoff configuration. Okay for short takeoff, so we assume we're going to burn some of that fuel and then land vertically. Typically you'd like a thrust to weight ratio of about 1.2 or so to give you that margin over that thrust to weight ratio of 1. If you're just right at 1, you really don't have enough control to be able to do a full vertical takeoff. So we have an engine thrust to weight ratio of 6. That means our engine output provides 6 times the engine's weight, and we have a design wing loading of 45 pounds per square feet. We're given a structural wing loading of the airframe of 15 pounds per square feet. So this is the empty weight of the aircraft. So notice that's pretty close to that 0.3 value. And we're given a fuel fraction of 0.4. That means 40% of the weight of the aircraft is made up of fuel. Now we're also given a payload of 500 pounds, and notice this is the first time a fixed number comes in for a given weight. Everything else is an estimate based upon a ratio of one of our design parameters. So using all these things, all these parameters, we want to estimate the wing area of the aircraft. Now you can mix and match these things, right? So this is just an example to give us an idea of how big the aircraft is going to be. Also, we're going to find the required fuel volume and the gross takeoff weight. So the first thing we do is we use that previous relationship of the takeoff weight, airframe, engine, payload, fuel, and we divide everything by the wing area. So now we're expressing everything in wing loading parameters. So notice we have a design parameter of our wing loading, and we can pull those off our benchmarking, right? We're already familiar that certain types of aircraft are going to have certain values of wing loading, so we can use that as a starting point for this calculation. Then what we can do is we can rearrange that to solve directly for the wing area, in terms of the payload weight, which is known, and these other wing loading values. Some of these were given, others we have to calculate, specifically the engine and fuel wing loadings. Now first for the engine, what we can do, since we're given things such as the thrust to weight ratio, the engine thrust to weight ratio, we can use some simple algebra where all we're doing for that engine wing loading, we're multiplying our weights. So we have a ratio of 1. So here's our engine wing loading right here, multiplying that by takeoff weight over takeoff weight, and our thrust over thrust. So that way we can then, at sea level, be able to find each one of these ratios, which are given a value of 6. So this becomes 1 over 6 for our thrust to weight of the engine. We're given a thrust to weight ratio of 1, and then we also have a design wing loading. So this gives us a engine wing loading value. Then we can do the same thing for fuel loading and calculate that value. So it gives us a value, since we're given a weight fuel fraction of 0.4, we can calculate a wing fuel loading of 18 pounds per square feet. Then we can throw everything together. We have these 4 values of wing loading, and we get a wing area estimate of 111 square feet. Now once we have that wing area, since we're already given a wing loading value, we can also come up with an estimate for the gross takeoff weight. In this case it turns out to be 5,000 pounds. Now this is not unreasonable given a payload weight of 500 pounds. 10% sounds like it's relatively small, but that's not uncommon for smaller aircraft, particularly ones that have a pretty high fuel loading. And it's also designed for a short takeoff and vertical landing, so you don't end up with having a whole lot of margin left over for your payload. Note, you can also use this equation to set bounds. For example, if you end up with a negative wing area, you know you've done something wrong. Those values don't make sense. So you can set a wing area equal to 0 and then solve for unknowns. And then we know that that is going to set a bound for that particular value. So for example, if we want to solve for fuel loading, we know that whatever value we get would actually need to be smaller to give us a positive wing area. Now that we have that, we can go back, we can find out how much fuel we need, and then we can find the volume of fuel based upon the density. So this is fairly straightforward. Again, notice that we didn't really throw any new physics here. All we're doing is using this very simple relationship of how we've defined these weights to come up with estimates. This is great for a starting point to be able to figure out an estimates for those actual weights that you get.